Good morning and welcome to this second dedicated webinar of the TEMPO project. First of all, I would like to thank you for being here, and I'm always glad to see such a technical and expert audience. My name is Gabriele Pesce and I will moderate today's discussion. For those who don't know me, I work for Euroheat and Power, the European Association of District Heating and Cooling, and in particular for its research and innovation branch, the DECE Plus technology platform. DECE Plus is the European hub for research and innovation in the district heating and cooling. Our strategy and final aim is to support our members through a series of activities to boost innovation in the sector, exactly like today. So today we are going to debate around the innovation and solution being implemented in one of the two demo sites of the TEMPO project, the small town of Windsbach in Germany, where a new network is being built and where some of the TEMPO solutions are being implemented. The discussion will be also the occasion to talk about networks in rural and more generally low density heat areas. I will not explain, of course, the characteristics of this kind of network, as this is a webinar designed for a technical audience. For sure, you all know much more than me. Suffice to say that finding solutions to improve the efficiency and above all increase the economic feasibility of networks in rural zone will be the real breakthrough of the district heating industry. As you might know, nowadays the share of district heating in the overall heating market is around 12%. Looking for a solution able to make the construction and expansion of heat network in areas where heat demand is low can really make the difference and turn district heating into a competitive technology in comparison with individual and often more polluting heating solution. Thus, I really encourage you to ask questions and share your comments. Don't be shy. So, before we get started, I would like to point out some practical technicalities. So first of all, hoping to make this as interactive as possible, feel free to ask questions. We are here for you. The purpose of this webinar is to explain, but also to inspire. We have around 50 registered participants. I don't think we're going to miss a question. On GoToWebinar window, you will find a question box. Please ask your question for the speakers there in the chat box. If you are having technical problems, please write them in the chat function. Questions about specific presentation will take right after the presentation of the speakers, and then at the final session of the webinar, we will have a Q&A debate and session. Lastly, webinar will be recorded and uploaded on our TEMPO website. So I now would like to kindly ask you, the speakers, to switch on their cameras so I can introduce them. So please, speakers, switch on your cameras. Okay, thank you. Perfect. So in order of agenda, Johan Desmedt, coordinator of TEMPO and project manager for energy technologies at VITO, who will present the TEMPO project. Then we will have Markus Euring, head of planners at ENERPIPE, who will explain the features of the Windsbach demo and its solution packages. The third speaker will be Davy Geysen, researcher for energy technology always at VITO, who will talk about decentralized buffers and CHP optimization. And last but not least, Romanas Savikas, Senior Energy Advisor at the United Nations Environment Programme at the Technical University of Denmark Partnership and Vice Chair of the group of experts, always in energy efficiency, always at the UNEP-DTU partnership. So I now would like to give the floor to the first speaker, Johan. So I kindly ask you, the older speakers, to switch off the camera. And please, Johan, the floor is yours. Thank you.
Yes, thank you very much, Gabriele, for the introduction. I can hope you see my screen.
Yeah, we can see.
Okay, thank you. Good. Thank you for the introduction. as Gabriele said, I'm the project coordinator of the Horizon 20 TEMPO project, and during this 15 minutes, more or less, I will take you with me to have a short introduction on the TEMPO project. So the TEMPO project is all about technology to decrease temperature levels in district heating systems. All right, and how can we lower the network temperatures? Well, if we lower the network temperatures, the benefits, of course, of this is that we have less heat losses in the district heating networks. We can have an increased share of low temperature sustainable energy sources. And we can also have an increased efficiency of the heat production technology. And for instance, if you have a heat pump system connected to a district heating systems, this will give you a higher efficiency of the heat pump system with lower temperature network systems. And how do we realize this lower network temperatures? This is a threefold approach. First of all, we do this by technological innovations, by business models, and by consumer commitment. So in the technological innovations, we will focus on the use of digitalization in network systems and also by optimization of the network and the building infrastructures. We will combine these technological innovations with business models who regard low recurrent temperature systems. The third one, and also highly important topic, is we want to commit to consumers by creating awareness and by involving them in the project. The Horizon 20 TEMPO project is an innovation action project with around 10 partners, and we have 6 technological innovations. These 6 technological innovations will be implemented in 2 demo sites, in 2 demonstration sites. One of them is a low temperature district heating systems, and the second one is a high temperature network systems. 2 demonstration sites are included in the TEMPO project. The first one is the Windsbach demo site in Germany, and the second one is the Brescia demo site in Italy. Our budget is around 3 million euros, and the project duration period is 48 months or 4 years. What are the technological innovations which we will implement during TEMPO? You have listed them here all on the screen. First of all, we will implement an ICT platform for detection and diagnosis of faults in substations. So as you know, a lot of these district heating substations do not function as they should be. We want to build a supervision ICT platform that can detect and diagnose faults on an automatical way. Second technological innovations is we want to implement visualization tools for experts and non-experts so that they can see what is their energy consumption, how they compare to others in the district heating system. The third technological innovation is dealing with a smart district heating network controller. And this smart district heating network controllers has 2 functionalities, that it can balance supply and demand in the network. And the second feature is that it can also minimize the return temperature in the district heating system. The fourth technological innovation systems is dealing with innovative piping systems. And this means that we will investigate to eliminate the bypass in district heating systems. So a lot of district heating systems and substations have a bypass network, and we want to implement an innovative piping system. The fifth one is the optimization of the building installation innovation. So if you connect to a district heating system, faults may occur, and often those low or high return temperature often have a cause in the building installation. So within that topic, we want to develop guidelines for an optimization of the building installation. And the sixth and the last one, technological innovation, is dealing with the decentralized optimal control buffers at the consumer side. And this is also the implementation in the Windsbach demo case.
Everything is fine, Johan?
Okay. The TEMPO objectives, sorry for that. The TEMPO objectives, well, they are listed here. First of all, we want to implement technological innovations in the low temperature networks and also in the high temperature network system. We will quantify also the benefits, and we want to calculate what is the benefits of our solution. We want also to empower the end users in the low temperature district heating systems, combine this with innovative business model so that we can guarantee a market uptake of the TEMPO solutions. Good, I will not give you too much into detail of the Windsbach case here in Germany, because other speakers will of course give you some more technical details about it. As I said, we have two demo sites. One demo site is the Windsbach demo site in Germany. This is a new built rural area with approximately 100 houses. Its energy supply is provided by a low temperature district heating network, and it's combined with a biogas fired CHP unit. The innovations which we want to implement here in the ENERPIPE demo is first of all a new version of a decentralized buffer system and an intelligent control of those decentralized and also centralized buffers. To give you a whole picture of the TEMPO project is that we also have a second demo site. The second demo site is located in Brescia in Italy and is under the responsibility of the Italian partner A2A. This is an existing high temperature network system, which is located in an urban area of a city in Brescia. And the research questions there that we impose or try to answer in TEMPO project, is it possible to decrease network temperature through the TEMPO innovations? So the main constraints there are we're dealing with existing buildings, existing technologies, existing radiators, existing substations, and small diameter connections. So the innovations which we want to implement over there are the supervision ICT platform, the visualization tools, the smart control, and an optimization of the building installation. This last slide wraps up my presentation for today. So I've given a short introduction to the TEMPO project, and I would like to thank you for your attention.
Thank you, Johan. So yeah, now we have a complete overview of the TEMPO project. Euroheat and Power, we are very proud to be partner in the dissemination and communication activity of this innovative project. So now don't waste time, and I would like to give the floor to, sorry, I don't know if there are some questions now for Johan. No, okay. So I will keep the general question for the last session of the webinars of today. So thank you again, Johan. Now I would like to give the floors to Markus Euring of ENERPIPE. They will explain us the Windsbach demo characteristics and the solution that are being applied. So please, Markus, the floor is yours.
Many thanks, Gabriele. Many thanks for the introduction. Yeah, Johan already has explained a little bit about the Windsbach demo. Now I want to show you a little bit more about our solution and our project where we are involved. So that you get a bit of an overview. So really what I'm talking about today is not about such projects. If you want to hear something about massive district heating, then it's probably the wrong session you have been in today. Today I want to talk a little bit more to such smaller projects in rural areas. Does mean projects with a low heat density in rural area projects or in new developing area projects. And perhaps you don't know ENERPIPE. ENERPIPE is a company which was founded 13, 14 years ago, and we are a German company with about 50 employees based near Nuremberg. And what we're doing is everything with district heating. So we are a system provider for district heating projects. So we are supplying district heating, pre-insulated pipes, the manifolds, heat interface units, buffer tanks, but also the control. So everything what you need for an efficient heat distribution. But we are not like a catalog company. We are also quite often involved in the design, in the planning, in such kind of projects. So lots of communities or some municipalities are in contact with us to develop such kind of projects. And that you get a better overview in general about our projects. So like this, a typical ENERPIPE project could look like. So really rural area projects with old houses which gets connected on the scheme. There you often have the problem, not everybody needs at the same time a new district heating connection. So already this is sometimes quite tricky because not everybody wants to be connected on a district heating scheme. And so we have quite often lots of meter of pipe, hundreds of meter of pipe, and sometimes the problem not so very, very big heat demand. And therefore we have developed some solutions which help to get such district heatings with these aspects even efficient. And this is quite similar in such rural area projects to such projects which are in new developing areas. So in this kind of projects, you have quite often, not the big distance from one to the next house. Quite often all these houses are connected to the scheme, but the heat demand is much less than to older houses. And so there's a quite similar problem. And our aim is to develop projects even in such areas and to get it efficient. So now I want to talk a bit more about our demo site in Windsbach. So Windsbach is probably not known for everybody, but I hope most of you know Germany a bit. And here is Nuremberg, as well as the place I'm living, and the company for ENERPIPE is as well in this area. And Windsbach is more in the south of Germany. It's a small town with about 6,000 inhabitants, and you can see here as well the area. And here in the gray area where the ENERPIPE demo stands as well is the new developing, or is a new district heating network. There are different phases. Johan already has shown you some slides on the slides before, some plan of the district heating network. But really in general, we are talking today about this area with about 100 houses which are supplied by district heating. As mentioned, there are different phases. So here see on top the plant room. Phase one was the first area which was installed with the pipes. Afterwards, or in meantime, also phase two is developed, and there's also a plan if all these houses are built to develop phase three. And also on the left-hand side, this was not really the initial driver of the district heating network. There are in this area a few houses which have just old oil boilers, and so the network operator has designed the network for this case that they also can connect this kind of houses. In total, we have about 2,600 meters of pipe installed for this district heating network, and as the heat source is in this case a mix of waste heat of a biogas plant. So really there was some heat available, but as well additional CHPs, and the backup boiler is there for the total heat production. We have in the plant room as well a central buffer tank with about 40,000 liters, but we also have some decentralized buffer, but I will explain this a bit later in detail, what this helps for this kind of projects. As mentioned, we are quite often in this kind of projects with a low heat density. Every red button is a district heating network, and you can see that there are some district heating networks with higher heat losses and with lower heat losses. But in general, you can see the higher the heat density, the better is quite often the network. Makes sense, because if you have lots of heat which you can transport or you can sell to your customers, and you have just a few meters of pipe, it's better than if you have the other way. So really, this is the reason why it makes sense that low heat densities networks are sometimes a bit difficult. But ENERPIPE, and we are quite often in our rural district heating networks on the left-hand side in this area in projects active. So we try to find solutions to get heat losses in this area about 10%, 15%, and not higher. And there we have developed different kinds of solutions. And there's just one thing what helps by such projects quite often. And that is to have in each house not a standard heat interface unit. Quite often we're using, in this case, decentralized buffer tanks. So in this case, you say, okay, why a decentralized buffer tank? On the left-hand side, you can see there's, of course, quite often in the morning, a peak load, which is necessary to provide to the house because of heating and domestic hot water. And if you don't have a buffer tank in the house, then you have to transport it through the pipe, and also with the plate heat exchanger. At that moment, the heat has to transfer from the district heating network to the house. But if I have not just a plate heat exchanger, if I have a buffer tank, you can really, you can make a peak load shaving of your maximum heat load, and this helps to reduce your maximum heat load, and this helps also to reduce the pipe sizes in the network. So perhaps before you have had 40 mil pipes, so you can go to 32 mil pipes. So really, this helps really as well as the network design. Here I can explain it again. So normally you have here plant room, you have a buffer tank, a pump, the pipes. You want to transport the house, the hot water to the houses with a plate heat exchanger, but instead of the heat exchanger, we install quite often such kind of decentralized buffer tank. The temperatures depends on the kind of houses which are connected. So the flow temperature is quite often between 60 and 85 in our projects. Of course, if you are in big inner city networks, you have quite often higher temperatures, higher than 100 degrees. And the aim is to achieve very low return temperatures. And with our system, we can achieve temperatures in the area of 30 degrees. So now you perhaps are asking, okay, plate heat exchanger needs not much of space. You're right. 600, 800, and a 1,000 liter tank is not so small. So of course you need more than 1 square meter of for such a kind of buffer tank in each house. And we know that this kind of solution works quite well, but we also know that it's not easy to get something installed in every house, especially in new built houses where there's often not so much space for technique. And this was the aim in TEMPO, where okay, we have a technique which works quite good, but we need a solution which helps as well to develop such new house projects with one family houses. And in TEMPO, was Johan already has told us in his first presentation, one of the innovative solutions is the developing of a decentralized buffer tank, which is quite small for one family houses. And this is the buffer tank. The buffer tank has just 250 liter here. And on top, you can see all other components like freshwater station, the pumps, everything what you need for the secondary site. So it's really a plug and play solution, which has just a space demand from 60 centimeters and a height of about 2 meters. So really a small plug and play solution, which you can bring into the house, connect it with the district heating scheme, and afterwards you can connect it to your underfloor heating, to your radiators, what else is installed in your house, and you don't need much more for your heating and for your domestic hot water in your house. So really it's a plug and play solution with not so much space available. If there's not so much space available, sorry. And another thing is possible with such a concept. So really it's not just you can reduce the pipe sizes, you can optimize the loading of your buffers. So something what David will explain afterwards in detail. But just I want to let you know how it could work. So really there you also have to install not just the pre-insulated pipes, you also have to install some cables for communication. And so if one house has, for example, some heat demand in summertime, you can load afterwards the other houses at the same time. So afterwards the pump can be switched off, and you don't have to pump your hot water all time through the network. Or if you say you have in winter time in the morning, 6 o'clock, a very big heat demand, then you have the opportunity to say, okay, I can load some buffers between 4 and 5, then other buffers between 5 and 6. So really, there's some opportunities to optimize the buffer charging. And you can see it here as well. The different colors are different houses. And if you see the peak, then the motor valve is open. So the valve is opened to charge the buffer. On the left-hand side, it's an uncontrolled loading. So every buffer can be loaded if there's some demand. And on the right-hand side, there's a control charging concept. So really, if I say, if one house needs some heat, I will charge other houses as well. And so I already have an opportunity to switch off the pump for a certain of time. This is, of course, more important for summertime because in wintertime, the pumps are more and more active because the buffer is not made for, in this case, it's not made for, to restore all the heat demand for heating in wintertime. I'm more or less ready with my presentation. I just want to show you some more impressions from the demo site in Windsbach. This was really from the beginning when the installers have installed the network. You can see, this was lots of pipes. This was on the right-hand side, the connection pipe from the waste heat AD plant to the plant room. And here on the left-hand side, you see some trenches with a main header and some connections to some potential houses. Here they have started with manufacturing the plant room and some other houses, so there was some progress ongoing. And after the plant room was built, you can see here the hydraulic with the buffer tank with different CHPs and a backup gas boiler. And here's as well on the top the heat demand, which is, well, not the heat demand, the heat which is transported from the AD plant. And here you can see two pumps. So one is ready for the new development area, and this is for the old area which I have shown you on the left-hand side, which will be also connected on the scheme. Here are some more pictures from the plant room. So you can see here the CHP, and here some more pumps already. These are some impressions from the Windsbach plant room. And in the end, you can see already the projects from the sky view. So here again is the plant room. This was phase 1. Here, in the meantime, phase 2 is already installed. Already most of the houses are built. And here in the end, there will be phase 3. And some perhaps have asked in the beginning, so is the buffer tank a solution which makes sense in one family houses? You need lots of space. Here you can see on the right-hand side how much space it is. Really, it's not so much. You can see you can integrate it quite easy in a room in a new family house. So many thanks. This was everything what I wanted to talk today about our Windsbach demo, about our decentralized buffer concept. And it's something what is for new developing areas, but we're also using such kind of technique also in rural areas where all the houses are connected. Many thanks.
Thank you very much, Markus, for your very interesting presentation. I hope that this gives a very good example of the feasibility of district heating in low density heat areas and the innovation that are being implemented in this kind of network. So in this case, we have already a question for you. Two questions, 3 questions. Okay, great. So the first one is, Markus, how do you do with service pipe? Do you know exactly where the house in B?
So I'm not sure if I understand the question completely right. So really, was it, perhaps I can show my presentation again, 1 second.
Yeah, please, of course.
Perhaps, is it meant, so like here, there's a house connection, and so they have installed the T piece and have installed 3 meters to the field of land where the house will be later. So you're right, we don't know exactly where the house will be. But for one family houses, it's quite clear that will be on the area 10 meters. And so quite often the T will go to the field of land where the house will build more or less in the middle. And because of the flexible pre-insulated pipes, you can bend it to the direction where exactly the house connection should be, or where the house technical ground will be in the house. I'm not 100% sure if I have answered the question right. I hope so.
Yeah, we got a clarification about question 1. Is the grid first and then the house built?
Okay. Yes, of course. Yes. Okay. So really, this is something which is quite typical for new developing areas. If we have project like this in Windsbach, before there will be installed a street or something, in the beginning, there's really the pipes. So really the header will be installed. Then you have 3 meters to the field of land where the house will be later. Then the streets will build, and afterwards the houses will build. So this is the reason why this is a technique how we use it in new developing areas. I have shown you in the beginning as well some projects. 1 second. Like here. Here is completely different. There the houses are built, and afterwards the houses will connect it to the scheme. So really, this is different between new developing areas and district heating networks where the houses are already installed.
Okay, thank you. I would like to pose you a second question, and then for the rest of questions, I would like to let them in the Q&A session. So just a second one, can the buffer tanks do priority switching for space heating and domestic hot water?
Yes, definitely. So really, there is priority given for domestic hot water. So really, the buffer tank, so in general, I have perhaps not explained it in detail. So really, the buffer tank is not filled with fresh water. So really, we have always a freshwater station which is connected to the buffer tank. And so if there's a high or if there are lots of showers are going on, so you can switch off the heating and just use all the available heat for the showers for domestic hot water. Yes, it's priority is given.
Okay, thank you, Markus. I know there are also other questions, but I would like to keep them for the Q&A sessions, also to give the other speakers the opportunity to present the slides. So for the moment, thank you, Markus. You will have other questions right after. So perfect. Now I would like to give the floor to Davy Geysen. Also from VITO, who is going to present the decentralized buffer and CHP optimization solution for TEMPO. Please, Davy, the floor is yours.
Yes. Yes, thank you for the introduction. So I will talk about the decentralized buffer smart charging algorithm and the CHP optimization that we've implemented in the Windsbach demo. So yeah, first I will show a short overview of the network. It's more of a simplified version than the one that Markus has just shown. Then I will talk about the CHP optimization. I will continue with the smart charging of the decentralized buffers, and I will wrap up with some conclusions and next steps. So here you can see a very simplified version of the network in Windsbach. So the most important thing to note here is that the heat production can come from several different producers. So you see there are 2 CHPs, but there's also a peak burner. Then we also have some heat coming in from a waste heat plant. And there are 2 large, big central buffers of 40,000 liter, so 20,000 liter each. And then connected to them are the buildings with the decentralized buffers. So most of them are the 250 liter buffers, but there are also some buffers that are 600 or even 1000 liter. So the first thing I will talk about is the CHP optimization. So as you can see, the CHP generates the heat for the network, but of course the CHP also generates electricity. And if we want to optimize the running of the CHP, we have one option, because the heat is sold to the customer on a fixed price, but the electricity that is made by the CHP is sold to an aggregator according to a real-time pricing signal. So what we want to do here, the goal is to operate the CHP when the electricity price is high, so we can sell the electricity to the aggregator at a higher price. How will we do that? So we use a model predictive control approach. So model predictive control is actually a method which can be used for controlling a process, and while satisfying a set of constraints on the inputs of the process and also on the state of the process. The main advantage of this model predictive control is that we can optimize for the current time step while taking into account future time steps, because we are using a model of the system. Here you can see an overview of the model prediction control approach that we've used in Windsbach. So of course, as the name already implies, it uses a model, which you can see here, the CHP and a buffer model. In this system, we use a linear model of the central buffers. So we are going to use the flexibility which is available in the central buffers to store the heat when the CHP is running. One of the important inputs for this model are the forecasts of the non-controllable inputs. And the non-controllable inputs in this sense are the total heat load of the network, which is something that we forecast based on a temperature, an outdoor temperature forecast, which we get from the Norwegian Weather Service. Then we also forecast the heat that comes into the system from the waste heat plant, and the heat that goes out of the system to the waste heat plant, because that's also possible. So once we have these inputs for the model, we apply an objective to this model. And as just said, the objective here is, of course, to maximize the price of the sold electricity. Also, besides this objective, we also need to put in some constraints, because the system has some constraints in which it has to work in. And for example, in our system, we have the CHP, which at this time there's only one CHP in operation, and the CHP is able to generate 250 kilowatt thermal heat output. So one constraint is that it's non-modulating. So we can either say the CHP is switched off or it's switched on at full power. That's the only possibility we have. Plus, once we switch on the CHP, it has to run for at least 2 hours. So you cannot just switch it on and off every quarter. For the buffers, the central buffers, we put two constraints, is that the state of charge, which we decide upon based on the temperature measurements of the buffer, has to stay in between 30% and 80%, because then we still have some safety left if it will go below 30%. And the buffers have to be on temperature in between 55 and 80 degrees. So once we put all this together, we get the optimization problem. So we calculate the outcome of this, and this outcome will be a plan for the CHP for the next 24 hours. So this plan, we can recalculate it multiple times a day. So at the moment, we recalculate the plan twice a day, so once in the morning and once in the evening. This is then mailed to the network owner, and he puts it into the system so that the CHP will follow this plan. The main advantage of being able to replan during the day is that, of course, our forecasts of the total heat load and of the heat input from the waste heat side are always off. They are never 100% accurate. So every time we recalculate, we start again from the real system state. And actually, in a later stage, it's even the case that we will be able to send our control plan directly to an API of the aggregator, so that we don't have to get the network owner involved anymore. So everything will run automatically. In the next slide, I will show you just one day of a result. This is a day from last year's summer. So the most important thing to see here is that the dotted lines, so the green and the red one, are measured lines. So the green is the power output of the CHP, and the red one, the red line, is the state of charge of the buffer. And then the blue line, the continuous line, is the optimal plan that we've generated. So that was the plan that the CHP should have been following. And the purple line is the price. So you can see that our optimal plan was planning to run the CHP when the prices have a peak. But you also see in the results that the CHP did not completely follow our plan, because you can see that at 6 o'clock, for example, here, it stops running. And while we said in our planning that it should have been running still for a couple of hours, this can happen because, for example, that the waste heat input was more than we expected or than we forecasted it. So the CHP had to stop running. Actually, this led to the following results. For example, for last year, during 4 months, if you look at between July and October, we saw that the average price of the electricity was 36 euro per megawatt hour for this system. And by sending our optimal plan and following the optimal plan, it is able to increase this average price, selling price, to 43.5, which maybe doesn't seem like a very big improvement. It's an improvement of about 17%. But if you then look at the spread of the price of the day ahead price, you can see that the prices are always in between, or most of the time in between 30 and 45 euro per megawatt hour. So if you see to the results, then yeah, it's clear that we maximized the profit, because if the spread of the price would be higher, we would also be able, of course, to increase the profit even more. So an important advantage is that we unburden the district heating owner, because before we did this in an automatic way, the district heating owner was putting in the CHP profile every morning and every evening himself by doing calculations, of course, from experience in the past, and seeing when it would be best to run the CHP. This now goes automatically. And it can also decrease the maintenance, of course, for the CHP, because we can keep into account all the constraints that are necessary on the CHP running time, so that we do not have to do, let's say, an emergency stop, because that's bad for the CHP. So continuing with the smart charging of the decentralized buffers, this is another control problem that we tackled in the system. So what Markus already explained is that the buffers are charging, but they are charging based on their temperatures. So for example, if a decentralized buffer reaches a certain bottom temperature, it will start charging immediately by the backup controller. This can lead to peak demands, because, for example, let's say in the morning peak, when everybody starts showering or is using hot tap water, it can happen that all the buffers are empty at the same time and they start charging simultaneously, which induces a peak demand, and this is something we want to avoid. So the goal of the smart charging is to reduce the peak load, and this time we will do it with the reinforcement learning approach, which is not model driven, but it's data driven, so it learns from data from the past. But before we could implement such an approach, there were some challenges that we had to tackle, because when we were doing the buffer response tests, we saw that, yeah, in the beginning we wanted to exploit the full flexibility of a central buffer, meaning that we would like to be able to charge the buffer according to a specific power profile. So starting, for example, with charging 10 minutes at 6 kilowatt and then charging 10 minutes at 20 kilowatts. And the idea was that this was possible in the system. But however, during our response tests, we saw that this could lead to a violation of the comfort constraints of the end user, which is undesirable, of course. And I have a small example in the next graph. So what you can see here is the light gray lines. So on top and the bottom are the top and the bottom temperature of the buffer. And the middle line is the middle temperature of the buffer. The orange line is the profile that we tried to put onto the buffer. So we wanted to charge the buffer at a slow rate, so 6 kilowatts. But what you see here is that at 7:30, for example, here, you see that there's a high demand for hot water, so the buffer temperature drops immediately. But because we have our 6 kilowatt limit here, the buffer is not able to recover from that. So normally the buffer should start charging here at full power, but because we put the limit, it doesn't do that. So this can lead to having a cold shower, which is of course something we would like to avoid. So based on the results of these tests, we decided that we will not cut the power of the charging, but we will only decide on the time when the buffer can start charging, and we will also always charge at maximum power. So also this behavior, this leads to highly, the charging behavior is highly dependent on the tap water consumption, because you cannot forecast exactly when users are taking a shower. So it's difficult to tackle this with a model-based approach. So this also leads to a high uncertainty of the next state of the buffer, because you don't know exactly when people are using the tap water. So then the reinforcement learning approach comes in. So reinforcement learning is actually an area of machine learning in which intelligent agents take actions in an environment in order to maximize their cumulative reward. So looking at a very simple example here, you can see when you try to train a dog to sit down when you give the command. So the dog is the agent in this system then, and it has two actions. So it can stand up or it can sit down. But when it sits down, the owner will give him a treat. So the dog learns from past behavior that, okay, if I get the command to sit down and I will sit down, I will get a treat. So this way, the dog will be able to take the desired action just by knowing the reward he will get for it. And of course, in our system, it's a bit more complex, but the idea is the same. So for example, in our system, the agents are, of course, the buffers, and they do have a state space, which is a bit more complex than the one of the dog. So the buffers have 3 temperature sensors. They give the current state of the buffer, but also historical readings to see if the buffer is charging or discharging. And also to predict the power demand of a decentralized buffers, we look at the historical power demand. So the last 10 times the buffers, the power demand of the last 10 time steps, and the time step is 10 minutes in this case. And then also the time since the last activation of the buffer. And the buffer has 2 actions, which is do not charge or charge. The reward function here is peak shaving. So we want to avoid that all the buffers start charging at the same time. So we put in a cost for a high power demand, and we also put in a penalty for a backup controller override. This happens when we do not charge the buffer, but it is empty and it has to charge automatically. So we did this by implementing a policy iteration approach, and policy iteration is actually a way to find the optimal policy for given states and actions of the buffers. And the policy then is a strategy that dictates the action that the buffer has to take when it is in a specific state. And to do this, it uses the notion of these rewards, but also a value function. And the rewards I just explained, but the value function is something more complex. It actually gives you an estimation on how good it is for a buffer to be in a specific state. So for example, if all buffers are half empty and you do nothing, there will be no reward, but there will also not be any penalty, because you do not induce a peak load, and you also you don't induce the backup controller. But if the buffers get more and more empty, you will end up having to charge them all at the same time. So this value function gives you an idea of how good the state is for future rewards. So we start with a policy that does nothing. So we leave the buffers as is. And then we can calculate the value function, which is actually the value function of the backup controller. So when you do nothing, the backup controller will make sure that the buffer is charged whenever it needs to, but it has a very low value function because that's not the way we want to charge the buffers. So based on this policy, we have the value function, and we generate a new policy, which is better. So we find a better action for every state, and this we will do in a lot of iterations until we find a policy that finds the best actions for each state. And this is given by the lower formula here. So we start with the policy do nothing, we evaluate the policy, then we improve it, we have a new policy, and then until the policy is not changing anymore and we have the optimal policy. This policy can be seen as a sort of a big lookup table in which the buffers can see, okay, I'm now in this state, so I have to take this action. The practical hurdles here are that we have a huge state space because we have a lot of buffers which can all switch on or off. So we have to limit the state space by looking at the historical states which were observed, and we leave out the other states which are possible but have never been observed. And also a huge action space, which we can limit by saying that, for example, not more than 30 buffers can charge at the same time, because that's anyway part of our peak shaving algorithm. So yeah, the unfortunate thing is that we don't have results yet for this approach, because we will start testing it this week actually. So I cannot give you any numbers on this yet. And to conclude, some challenges in the system is that, as Markus also said, the system is constantly having new connections to the network. So this means that the data that we have to learn our algorithms and to learn our model, they are always running behind, because every month new buildings get connected, and so the total heat load in the system gets increases. Which is difficult to forecast all the inputs we need. And it also leads to data interruptions, because sometimes when they are connecting new buildings, they switch off the communication for sending the measurements. And then more in specific for the CHP optimization, due to unforeseen events, it's difficult to forecast the heat load coming in. For example, this waste heat plant, it's very difficult to forecast how much energy it puts into the system, because this changes daily. And also sometimes there's some maintenance on the heat exchanger, so then the heat input drops immediately to zero. And all those things which we don't know upfront make it difficult to make a right forecast. Next step for the CHP optimization is that we have to extend the model predictive control with the second CHP, which should be taken in operation actually in February. And also we want to automate the control plan, sending the control plan to the API, because now we still send it to the owner, which has to do a manual check. And then the last thing for the smart buffer charging, we saw that, yeah, it has limited flexibility because it's only a 250-liter buffer in most houses. And the backup controller is running there, which is a good thing, but it also kicks in if the temperature goes below a certain value. So let's say the flexibility in time that we have to start charging the buffer earlier or later is not that much. It's around 1.5 hours that we can choose to switch the charging of the buffers. And of course, yeah, because we are also controlling the bypass valve with our profile, we cannot use the full flexibility of the buffer, because we would violate comfort constraints. And the next step, of course, is to test this reinforcement learning approach in the real system in Windsbach. So that concludes my presentation. And thank you for listening. And if there are any questions, I would be happy to answer them.
Thank you. Thank you, Davy. I think this was really the technical core of all the webinar. So yeah, for the moment we don't have a specific question, so I will let them in the Q&A session. And we are really running out of time, so I would like to give the floor immediately to our last speaker, Romanas Savikas. So thank you again, Davy. He's going to present a very interesting study on double loop network for combined heat and cooling low density heat areas. So please, Romanas, the floor is yours.
Good morning, everyone. Can you see my screen well?
Absolutely, yeah.
Okay, thanks. Yeah, I would like to give thanks to all presenters presenting all these sensitive topics for low energy density heat areas. I remember some years ago we were talking, okay, is this heating viable is in these new developed areas and low energy density areas, or do we have to compete with gas network, or is it at all economically viable solution? Now I see a huge potential for these new developed areas, low density areas, multi-flat buildings, even one family buildings. Yeah, so many thanks putting these all problems on the plates and finding right technical solutions and showing how to make it happen in reality. From my side, I work in UN organization network, developing DC heating and DC cooling activities in different countries, cities, regions. So I would like to share some innovative solutions for low energy density heat areas, about double loop network model for combined heating and cooling. So the main idea can be presented in this picture. It's a double loop network. It's an innovative model in which operated with ultra low supply and return temperatures, about 45 supply and 25 return temperatures. It's mainly for low heat energy density areas. In Denmark, this solution was compared with a typical tree network and with individual heat pumps to each end user rather than distinct heating networks. And double loop network is actually, it's a pump driven system where the separate circulation of supply and return flow increases the flexibility of overall system. So integration and displays of heating and cooling energy becomes much easier. And you can see in this picture the main idea and model of this double loop network, and all these flows, supply and return flows, they are separated and can flow in different regimes. Despite the increase of central and local water pumps to operate and control systems, energy consumption was about 1% for pumps from the total energy consumption, and this was also an advantage at the design stage of a larger pressure gradient and was related to pipe diameters. And you can see in the picture what is the profile for double loop network and for tree network, and what it makes the difference in between for these networks. For the house installations, the installation of electrically heated insulated micro tanks of about 10 liters each on the primary side of each building substation as a supplementary heating solution. So to meet the comfort and hygiene requirements for domestic hot water, I've seen questions about Legionella, so for our participants and presenters. So this will solve all problems and issues related with Legionella. As you see from the supply network, if you can receive 45 degrees, so you increase temperature, and also with this 10 liters micro tank, you can boost temperature and solve these issues. Despite increased capital cost, which increases about 5%, the integration of micro tank in the substation of each end user, you have two main advantages. So first of all, the possibility to use ultra low temperatures and avoidance of keeping these service pipes warm during the summer operation or when no load periods. So disadvantages in combination with possibility to circulate the supply flow without the need for bypass valves. This helped to minimize the distribution heat losses and achieved the average return temperature about 23 degrees, what is quite good result. Further studies documenting that no risk Legionella bacteria with lower set point temperatures for this domestic hot water preparation system can be found. Here you can find the schematics of connection of groundwater heating and cooling system for double loop network. Here you can see connection of cluster of 150 houses to the main loops and how it works and how it can be connected. And here you can find a comparison. So this combined with supply water circulation in this loop network served as technical solution and removed the need for bypass valve, as I said before, during summer periods. And double loop network reduced distribution heat losses from 90% to 12%, what is also quite a good result, talking from total energy consumption. And also return temperature decreased from 33 to 23 degrees compared to the tree network. While excess heat recovery can be limited due to hydraulic issues in the tree networks, and we know these issues and problems when we have excess heat, but you still have tree type network. So the double loop concept for scenarios like this with heat source temperatures of 30 or 45 degrees can help to solve these issues. This double loop network is cost competitive when we're considering the required capital on operating cost. And this network outperformed individual heat pump solutions. What we see like very hot topic comparing should we install individual heat pump or should we switch to distinct heating network. So also it for low density areas when waste heat was available locally, so it shows very positive and good results for a final customer. And finally, of course, in Denmark, the residential cooling is becoming as priority in some cases. So the potential exists of embedding heating and cooling in the same structure. And we can utilize this double loop network. Yes, and as I told, another key element of the future competitiveness of our district heating network and district heating and cooling network technology will be the ability of networks to integrate decentralized heat sources and to recover heat excess heating and cooling. So by double loop, we can solve these issues of integrating low energy potential or waste heat energy into the district heating network. And we can have uniform pressure and circulate both supply and return water flows separately to receive results. And when we're comparing individual heat pumps and district heating network, the use of individual heat pumps as an alternative solution for low heat density areas indicated that district heating networks could be competitive, and that is because the higher achieved efficiency of larger heat pumps and capability of recovering waste heat, and increased the cost efficiency because of economies of scale. It's also possible to separate circulation of supply and return flows in the double loop network. So proposed concept is able to supply 1.4 kilowatt of cooling to each end user, and that corresponds to about 50% of the total designed heat load of a double loop network. As due to promising results, the double loop concept is going to be further investigated. It's a very interesting method, and it's going to be investigated with a focus on climates where cooling demand is dominant, and compared to heating, heating demand. This model and pictures what you're seeing is more based for heating, but the same model can be applied and for cooling, and this will lead to a different approach and optimization of the system depending on availability of local cooling sources, the overall network design, which will be passed on peak cooling demand and lower delta T, integration of waste cooling energy or cooling prosumers to the same double loop network. So that's all from my side. Thank you.
Thank you, Romanas, for your very interesting solution. It's always very useful to have, say, an external point of view. So now I would like to inaugurate the Q&A sessions. We have already some questions that are unanswered, but for the moment I would like to also ask the speakers to switch on their cameras so we can have a direct, say, vis-a-vis. Okay, thank you. Johan, okay, thank you. So yeah, now I will give the priority to the all questions. So I hope to address the right question to the right person. The fourth question was, I think, addressed to Markus. In the meanwhile, I'm speaking to the attendees. You can also ask questions on the question box that you have in both webinar. So, do you have, Markus, do you have same service way for EL? I don't know, sorry, I'm not an engineer. I don't know if EL is an acronym, and water, so maybe heating and water. You are muted, Markus.
I think it's electricity, what is mentioned.
Yeah, of course, yeah, electricity, yeah. You're right.
So I think the question is really if there's the same trench, electricity and water. Yes, in the same trench we have both, but not exactly next to not exactly next to the tree. There's a distance of 40 centimeter, 80 centimeter. What else? So there's some restriction where you have some distance between the different kind of service pipes or electricity and water, for example. But it's quite often that you use the same trench.
Yes, maybe I have a question for all the speakers that is related to this electricity topic. Maybe so it's not just you, Markus. If the other speakers feels like to reply, maybe feel free to do that. So in some recent studies, this reheating system should be marketed, they say, to new customers with additional benefit, in particular in low heat density areas. So sometimes the solution can be that the district heating can deliver part of the energy which to date has been supplied by electricity. So to I would say replace heating with electricity. So one example, for example, is application in white goods. What do you think this kind of solution to make the district heating in low density heat areas more say competitive and also attractive for customers? I don't know if you get my question. Yes, no? To everyone.
Well, Gabriele,
maybe you didn't hear me. Hello?
yes, we hear you.
Okay, did you get my question?
Yeah, Gabriele, short answer from my side. I think that a lot of district heating systems are eventually also looking at the concepts or models to increase their business model, so to connect to much larger number of customers. And indeed, there are a lot of looking at additional business models, and for instance, providing them with additional services, maybe electricity, an increased or a better electricity tariff or a better heat tariff, combining with other components is very innovative and interesting topics, where we also looking this in the TEMPO project. So definitely this is worldwide to investigate further on.
Okay.
Another thing what I can add is in general in Germany, you see, of course you have cost for the plant room, you have cost for the pipes, but really one thing what is quite expensive is the civil engineering. So really quite often you can combine the district heating installation perhaps with some new streets which are or should be made anyway, or if you have installation of fiber optics. So really the civil engineering is quite expensive, and if you can combine such projects, then you have a better chance to realize such kinds of district heating networks in rural areas.
Okay, thank you. So let's go on with the other question, I think, to Markus. There are two questions actually. Someone wrote, I didn't understand if the tank is on the primary or secondary side, and this solution decreases heat losses in the distribution pipes, but I imagine it creates some heat losses in the tank. Is the overall amount of energy needs reduced then? If you want.
Yes. Perhaps can I share my screen again? Is it possible?
Yeah, please, of course.
Perhaps I just want to, then I can explain it a bit better again. So you're right, I haven't explained it in detail. For the origin projects or the buffer tanks, already there was the storage on the secondary side. So really before we have had a plate heat exchanger for the bigger houses, what you can see on the left-hand side, or a coil heat exchanger, but in this case it was both. The heat exchanger was before the buffer tank. So there was 2 times a heat exchanger, once to bring the heat in the buffer tank, and after you have had the heat exchanger for district heat for the domestic hot water with the freshwater station. And this was also one aspect which we have optimized in our new version. So already in the new 250 liter Calderon buffer tank, there is primary water stored. We have as well 2 heat exchanger, but they're not in parallel. They are on top of each other. So already one is for going out for the freshwater station, the other one is for the heating application. So already this is an improvement, so you can, or you don't have the delta T for 2 heat exchanger. So both options are possible, but of course it's better if you can store primary water. And the other question was concerning heat losses or overall heat consumption. So really, we have also done some measurements. So if you have normally a plate heat exchanger, a standard domestic hot water boiler, there we also have heat losses. And so we have compared these solutions, and there's not really a difference between both solutions. And also if you have not a domestic hot water boiler in each house installed, if you have like a combined heat interface unit with two heat exchanger, you have all the time the hot water on the station. So really there's as well all the time temperature on the plate heat exchangers, which has as well lots of heat losses. So really this both concepts should not have a big difference in heat losses. And also there's a difference if you have the heat stored inside the house. Of course, this effect makes much more sense in winter times than in summer, but it's not a lost energy, which is the problem what you have with pre-insulated pipes underground.
Okay, thank you.
Maybe to add to that, Markus, because I see in the question it's about the heat losses moving maybe from the distribution pipes to the tank. Of course, with the algorithm that I just explained of smart charging of the decentralized buffers, this is part of the algorithm that you move the heat into the buffers probably earlier than you would have done in a normal way. So in that case, you put maybe more heat losses in the tank than you would have without the smart control algorithm. But on the other hand, that gives you the profitability that you don't have a large peak, which then also has this impact on the heating price, of course.
Yeah, and perhaps I also can explain on this slide the next question, because I've seen there was a question concerning Legionella problem. So we are not storing any fresh water, so it's always with a fresh water station. And with our temperature, which is in this kind of networks quite often about 65, 60 degrees, there is not really a Legionella problem, because we are not storing water, fresh water. So really everything will be produced with the freshwater station just on time if there's some demand.
Okay, thank you for replying also to the Legionella question, and for the clarification. So I'm not following the order of question. I would like to give all the speakers the opportunity to reply to the question. So a question for Romanus. Could you speak more about the efficiency differences between individual heat pumps and the double loop district heating? Individual heat pumps are being marketed very aggressively, so I would like to know more.
Okay, very good question. We know these issues, and the competition is quite intensive, and from electricity and gas suppliers and district heating, we have our sector role. And first of all, I would like to bring that on policy level, on national government level, because everything today switches to electricity. And if we will bring everything on electricity, all consumption, industry, residential consumption, electric mobility, to charge all vehicles and everything on all network, we will face the same problem like we have today as fuel. And we finally find out that we have to use fuel diversification. So in this case, we have to bring on national government policy level to talk about energy supply diversification, not putting everything on electricity. We have to diversify supply of energy. That's one question from policy level. Talking about efficiency, first of all, economy of scale brings this efficiency to higher level. If you use individual heat pump, so then efficiency is smaller. When we use one big pump for central production, efficiency is much higher. Plus, when we run with heat pump, it runs more stable on different regimes, so we can manage better coefficient of performance, for example. Also, simultaneity brings us lower capacities. So when you install heat pumps in your apartment or your one-family building, simultaneity coefficients brings that you need less capacity for DC heating network energy source. So capital investments are much lower. So you have to bring everything on a plate and compare apples with apples. And of course, the integration of waste energy is very important topic. And when we're integrating waste energy, it becomes even more attractive. Yeah, so thanks for this question.
Thank you, Romanas, for replying. So, other two very straightforward, simple, say, questions. What pressure is the system, 16 bar, and what is the tap water temperature? I don't know who wants to reply.
So the question is focused on Windsbach project or for Romana's project?
No, sorry. I think this is not specified. So I think some form of Windsbach solution.
Okay, so really, I just can say from Windsbach. Windsbach is a fully installed plastic pipe system. In this case, it's a PN6 pipe because there was not necessary to go for higher pressure. Of course, there are reinforced pre-insulated pipes available. You can go up to 10 bar, up to 16 bars. There's some special pipe which is made for such application. But here in Windsbach, it's just with 6 bar, and it's absolutely enough for such kind of project. And concerning tapping waters, already it's up to the client, so they can say what kind of tapping waters they want, but it's mainly 50 degrees and not higher. But there would be an option to get higher temperatures. Of course, the primary water has to be higher as well, but in general, with this kind of buffer tank, it would be possible to have as well higher tapping water temperatures.
Okay, thank you, Markus. One last question from the audience. I suppose it's addressed to Davy, but if the other speakers want to reply, it's fine. How often do you need to communicate with our system? I think it's
so.
Yeah.
So what we do is we get the measurements on a 10 minutes basis. So the measurements from Windsbach come in on a 10 minutes basis. Can be faster, would be even better, but 10 minutes is fine. And we communicate also every 10 minutes, but we can do it faster. For example, if we do an optimization now, we can come up with the charging actions for the buffers for the next 5 minutes. So let's say if we are now at 11:57, we will put an action at 12. So it's not seconds based. It's more 5 minutes, 10 minutes based. Yeah.
Okay, thank you, Davy. So as we are running out of time, I would like to ask a very general question, also to give a good message to the audience. So in your opinions, very shortly, can rural district heating actually competitive compared to the individual heating system, and which are the most important aspects to address? Very shortly. I know there would be, it would be a very long reply, but yeah, just a few thoughts about that, and a closing remark from Johan. So wanna reply to that?
Yeah, for example, if we showed it with all the different innovations that we add to it, I think it's possible to make it profitable just by adding everything together. So it's not just one aspect that will make it profitable, but if you add like the CHP optimization, you add the decentralized buffers and everything together, I think it will it makes it possible to have these kinds of systems. And I think that's also what ENERPIPE is doing all the time. So and I think they are successful in it. So
absolutely, I can agree what Davy has said. It's already our main project are in projects like what they have heard today, and of course we have to check it quite strict from the beginning. So really you have to calculate the heat demand from the beginning if you have existing houses. And as mentioned, it's not just the pipe, it's not just the control, it's not just the heat interface unit. So really the total system has to match ideal to each other, and then such a project can be realized quite successful. And also, as mentioned before, sometimes we have waste heat which is available from a biogas plant, from what else. So these are all different in each project, but this helps quite often to make a project more efficient. Of course, not just efficient, as well more economic for the network operator.
Thank you,
and
Markus.
of course, if we have CHP and we produce electricity, we still have heat. If we have waste incineration, we still have heat. So we have give a chance to consumers to utilize this heat efficiently. Otherwise, if we have CHP producing electricity, we still have the heat.
Thank you. Johan, some closing remarks, and then we can say goodbye to everyone.
Okay, from my side, some closing remarks. I want to thank the audience for participating in this session. In this online webinar, we have seen a lot of good questions in the Q&A. So thank you all to the speakers to have the time to participate in this webinar. Thirdly, thank you also Euroheat and Power, Gabriele and Oksana, for setting up this online webinar, the organization. It was a really good webinar. I would also like to invite you to follow us on Twitter, LinkedIn, and to visit our website, because from now on, we are more or less in the end phase of the project. Within a couple of months, we will also publish public reports and deliverables and some news on our website. So it's much appreciated to follow us on Twitter, LinkedIn, and other channels. If you have questions, you can still ask them. We will answer them by email, I think. And I would also like to invite you in May, beginning of May, there is a Euroheat and Power Congress at the beginning of May, where we have a specific 2 times workshop on TEMPO, besides the other Euroheat and Power topics which are also there. So I would like to ask you to participate also in that online and also offline congress. It was a very fruitful technological discussion. I think we can have a long debate on this even in the afternoon, but for this it's noon. I wish all to thank you for participating, especially in those times. Stay safe, keep care of each other, and see you on the next occasion, hopefully physical, and all the best to you. Bye, and thank you for participation.
Thank you, Johan. Just thank you for your nice words. And just a final reminder: the recording of the webinar will be published on the Euroheat and Power channel and on the TEMPO website. Thank you again, and have a good lunch.
Thanks. Bye-bye.
Okay.
Bye.